Log on, tune in, find out. Another good idea from Cambridge.
Yep, okay. Okay, so today I'll be talking about classification of stability conditions on curves and surfaces, and it's actually just the classification of hearts of stability conditions on curves and surfaces. And I really want to do computations. I mean, I'll leave out some details, but essentially I'm doing all the computations. And I start out with a case I've talked about yesterday already. So this is the case of a curve. So C, smooth projective curve over some algebraically closed field. And there were these two, the theorem, which is due to Bridgeland originally, then a better proof provided by Macri, saying that if sigma is a numerical stability condition on the bounded derived category of coherent sheaves on C, then there exists a phi such that the heart at this point, so the category that is spanned by all semi-stable objects with respect to this numerical stability condition, whose phase is between phi and phi plus 1, this then is the Abelian category itself, which sits in the derived category. And there were these three steps, and the one in the middle is the one I want to explain now in detail. And this says that all points in X, then the associated point sheaf is sigma stable, and similarly all line bundles on the curve are sigma stable. Okay? And I break this up into steps. So the first step is I take a coherent sheaf, and I suppose that I have an exact triangle A, E, B. So this is an exact triangle. So E is a sheaf, but A and B are complexes. And I suppose that there are no homomorphisms from A to B shifted by E for E is smaller than strictly for E negative. So if there are no morphisms, so no negative X between A and B, then these A and B's, the A and B cannot be arbitrary complexes. They are concentrated in 2 degrees. Then A is isomorphic to A0 plus A1 minus 1, and B is isomorphic to B0 plus B minus 1, 1, where now the AIs and the BIs are actually sheaves. So the thing I've not recalled here was saying that for all objects in the derived category, every object is isomorphic to the direct sum of its shifted cohomology sheaves. So the AIs. This is actually true for any abelian category of global dimension at most 1. And so we know that these objects A and B can be written as direct sums of shifted sheaves, and under the assumption that there's an exact triangle and no negative X between A and B, then they're actually concentrated in 2 degrees. So A is concentrated in degree 0 and 1, and B in degree 0 and minus 1. Okay. Up to? No. No. Well, we see the proof. No. That's because, I mean, that's somehow fixed by being in the exact triangle with, right. So if I have an exact triangle like this, then there exists a long exact cohomology sequence So if I start in the middle, then I have the cohomology of EE is an object in the abelian category. So H0 of E is E. And then there comes H0 of B. Then there comes H1 of A. And then all the other cohomologies of E are trivial because E is concentrated in degree 0. And that means H1 of B is isomorphic to H2 of A. And if I continue in this direction, then H minus 1 of B. Then there comes 0 here. And after this, I have again Hi of B is isomorphic to Hi plus 1 of A for all I that are not minus 1 and 0. Okay? And what I have to show is that actually this implies that not only that they're isomorphic, that they actually vanish. Okay? So I have to show that these groups are 0 for exactly I not 0 or minus 1. Okay? So suppose now HIB is non-zero for some I. Then I have this isomorphism, but on the other hand, I know that A can be written, so this is this first claim here, as its direct sum of its cohomology sheaves, and similarly B can be written as a direct sum of its cohomology sheaves. And if I have an isomorphism of something non-trivial here, I can get an isomorphism, a non-trivial homomorphism from one of these direct summons to one of these direct summons here, and that means I get an morphism from the direct sum to this direct sum and with the appropriate shift. So let me see, I have HI A plus 1, plus 1 A shifted by minus I plus 1 to HI B. So this cohomology sheaf is isomorphic to this cohomology sheaf. So if I shift them by the same amount, then they're still isomorphic. So this group is non-zero. There's a homomorphism like this. But now this is a direct sum of A, and this is a direct sum of B shifted by minus 1. So that means there's a homomorphism from A to B shifted by B shifted by minus 1, but by our assumption was there are no negative x from A to B, and hence we get a contradiction. Okay. Yes, it seems so. Yes, indeed. So the second claim is the following. If I in the same situation, I start with a covariant sheaf and I put it in an exact triangle. And now I assume that there are no x for all I small or equal to 0. So it's a bit stronger. I also assume that there are no morphisms from A to B. And then I actually claim that A has to be a sheaf. A and B both are sheaves. Okay? So before, under this, the weaker assumption, they could still be concentrated in 2 degrees, and now under the stronger assumption, they're actually concentrated in 1 degree, in which necessarily is degree 0. Okay, so why is this? Well, it's essentially the same argument. Let me see. Yeah, so I write out this long sequence I have there. So I have this sequence. Let me write this as B minus 1. B what's my notation? B minus 1, A0, E, B0, A1, right? So if B minus 1 is non-zero, so I want to show that actually B minus 1 is 0 and A1 is 0. Then they are both sheaves. So if B minus 1 is non-zero, then this morphism here is clearly non-trivial. Right, because this is an injection. So these are now sheaves. These are the cohomology sheaves of A and B. And now I use the assumption that I'm on a curve of genus, positive genus. So positive genus assures now that I also have more non-trivial morphisms from B minus 1 to A0 tends to the canonical sheaf. Right? And now I use duality to get that there's a non-trivial x1 from A0 to B minus 1. And in the same fashion as above, this implies that there's a homomorphism because these are direct sums of A and B, that is a non-trivial morphism from A to B, which contradicts our assumption. And similarly, you prove that A1 non-zero would again imply that there are morphisms from non-trivial morphisms from A to B, which again would be a contradiction. Okay, so here you see clearly where the assumption on the genus comes in, and it definitely fails for the projective line. Okay, so these are the first two steps. Now let's look at Kx and L. So L always a line bundle, Kx a point sheaf, and I now show that they're actually semi-stable. It's not quite what I want. I want actually stable, but let's prove that they're semi-stable. And I apply 1. So for instance, for Kx, I take the first step in the Harder-Narasimhan filtration. So A equals A1 is the first semi-stable factor of E, and B is the cone. So I get this map, this map from A to E, and then I take the cone. And now using the Harder-Narasimhan filtration ensures that there are no homomorphisms from A to B. Why? This is the first semi-stable factor. All the phases of all these semi-stable factors of B are strictly smaller. So there won't be any homomorphisms, and even less for negative x. Okay, so this is important. This is the standard trick. You take the first bit of the Harder-Narasimhan filtration, take the cone, and then there won't be any morphisms from here to here. And now I can apply this the second one here, and find that A and B are actually sheaves. Okay, so in both cases, this works for any E, but now I look at the case where E is Kx. Then I get a short exact sequence. So this exact triangle in the derived category becomes a short exact sequence in the abelian category. A, Kx, B, 0. This is a short exact sequence in the abelian category of coherent sheaves. But this is a minimal object in this category. The skyscraper sheaf concentrated in one point doesn't have any subsheaves. Okay, except, I mean, the trivial one, 0, or the sheaf itself. So that means B, since we chose the A to be the first semi-stable factor, the B has to be 0. And this means Kx is 0. Oh, maybe I should have said in these first two steps, they actually, this is actually an argument of Gorodintsev, Kuleshov, and Rudakov. So you don't find this explained in Makria Bridgeland, Rudakov. You have to go back to their paper. Okay, so similarly for yes? Sorry. Thank you. So for the line bundle, well, you have the same argument. I still have this short exact sequence, but now the line bundle is not the minimal object in the category. Line bundle certainly has subsheaves, but what are the non-trivial subsheaves of a line bundle? They're again line bundles, and the quotient will be a torsion sheaf concentrated in some points, right? So hence B is torsion and A is a line bundle, but they are clearly non-morphisms from any line bundle to a torsion sheaf as long as this is non-trivial. So this is either this is 0 or B non-zero, or B is 0, because there's always a morphism from a line bundle to a torsion sheaf. And but this contradicts our construction. So here this is a contradiction. Hence B is again 0, and this is again implies that A equals L, and this means the line bundle itself was semi-stable. Okay, so let me finish this, and then we have really seen a complete proof of it. The last but not least, I want to show that actually Kx and L are stable. So we know already that they are semi-stable, and then this was one of the first exercises I gave you. They exist in an exact triangle A to Kx to B, such that there are no homomorphisms from A to B, and all A and B are both semi-stable, and all semi-stable factors of A are actually isomorphic to the first, all stable factors are isomorphic to the first stable factor of Kx, isomorphic to A1. This is the first stable factor of Kx. Right? So I'm using now the Kx and they are semi-stable. I've shown this. Then I use the existence of Jordan-Hölder filtration. So there's a finite filtration. I take the first stable factor, and then I try to put as many copies of the first stable factor in this A here, until there are no more morphisms from this fixed stable factor A1 into B, and that implies that this one is 0. And now I can again use the same argument as before. So as before, this implies that that A and B are sheaves, that this is actually a short exact sequence, and using the minimality of Kx, I find that B has to be 0, and that means Kx is actually isomorphic to A. But now A has only one semi-stable factor. Okay, it's always the same. One stable factor, and this implies that if I look at the element of Kx in the Grothendieck group of C, which is isomorphic to Z plus the Picard group of Z, actually let me do this in the numerical Grothendieck group. Then this is actually Z plus Z. Then this one equals, so this can be filtered by stable objects where the quotients are always the same objects. This is then n times A1. Right? But what is the class in the numerical Grothendieck group defined by the point sheaf? Well, this is just 0, 1. This is the rank, this is 0, and that's its degree, which is 1. But 0, 1 cannot be written as n times any other class except for n equals 1. And this means A1 appears only once as a stable factor of A. That means A is actually stable, and hence Kx is stable. And you argue similarly for the L. I'll let you just think 2 minutes. That's fine. So it's, I mean, in the end, it's elementary, so you have to come up with this trick, and then you're done. Okay, so this is the curve case, and now I pass to the surface case. So in the following, X will be a smooth projective surface. Again, can work over an algebraically closed field, or you can also look at a compact complex surface. I will fix a real number, which I call beta, whose real meaning I'll explain later, and I'll fix a class. So now this depends on the context. Either I want this to be in the Néron-Severi group and I allow myself to real coefficients, or in the compact complex case, I assume that this is a real 1-1 class on X, and I want to assume that the class is Neff, or at least Neff. So, for instance, you can think of an ample class or Kähler class on if you're on a compact Kähler surface. Okay, so I fixed the number and the omega, and now I define a torsion theory for the abelian category of coherent sheaves on X. I mean, very much in the same way as I did this for curves. I say T, so this depends on omega and beta, will be the additive subcategory of coherent sheaves, such that for all torsion-free quotients, non-trivial torsion-free quotients, the slope with respect to this class is bigger than beta. So here I forgot to say this. So I define the degree with respect to omega by the usual cup product of omega and the first Scherren class, and the slope with respect to omega is then the degree divided by the rank, which makes sense, which is this quotient makes sense for torsion-free sheaves, non-trivial torsion-free sheaves. This is the torsion part of the torsion theory I want to define, and then I define the torsion-free part as by the condition that E has to be torsion-free, and for all non-trivial subsheaves, I want that its slope is small or equal to beta. Right. So this is complete analogy to what we've done for curves. Okay, and this really defines a torsion theory. Sorry, and let me denote the tilt by A omega beta. This is the tilt of the the abelian category of coherent sheaves on X with respect to this torsion theory. Okay, so once I fixed the B and omega, I just write this as T and F. Okay, so that's the same definition as in the case of curves. Okay, so let me motivate this this definition. I mean, first of all, it's analogous to the curve case, and why not trying the same thing that worked so well for curves? The second remark is sometimes you can actually use this heart as the heart of a bounded T structure, as the heart of a numerical stability condition on X. So sometimes, I'll talk about this later, sometimes there exists a stability condition on A omega beta. Somehow today I would pretend there is one, that there are stability conditions on X, and then classify them under a certain condition and show that the heart has to be this one. Okay? But to actually construct them, you construct a stability function, you have to show that it satisfies all the properties. That's work. Maybe as another motivation why this category could be interesting. So recall that the minimal objects in the abelian category of coherent sheaves, so these are the sheaves without any subsheaves. These are just the skyscraper sheaves. So X a closed point in X. The minimal objects in this category, they can also be classified. They're either isomorphic to point sheaves, or they're isomorphic to shifts of mu stable vector bundles. So E is a mu omega stable vector bundle of slope, the given slope beta. So it's slightly more interesting. There are more minimal objects in this category than in the standard abelian category of coherent sheaves. And then last but not least, I'm sorry, this is, maybe I should say this. This is for K3 surfaces here. And last but not least, recall that there's an old result by Gabriel that says that two varieties are isomorphic if and only if their abelian categories of coherent sheaves are isomorphic, are equivalent. If you want to do this over a fixed field, then you have to require this equivalence to be K-linear. And here for projective K3 surfaces, you can show X and X prime projective K3 surfaces. One can show, maybe I should say one thing before. We know, of course, that there are varieties. So this statement says that the abelian category of coherent sheaves determines the variety. But of course, we know there are examples where the derived category does not determine the isomorphism class of the variety. And for K3 surfaces, you can actually prove that these abelian categories do determine the derived category. So dBx is equivalent to dBx prime if and only if there exists omega beta on X and omega prime beta prime on X prime, such that the abelian categories on X and on X prime are equivalent. Okay, so in some sense they play the role of the coherent of the abelian category of coherent sheaves if instead of the isomorphism class of the variety you look at its derived category. Okay, maybe one other word, I won't write this down, for curves, for elliptic curves. These tills of the standard tills of the abelian category of coherent sheaves can reinterpret it in terms of the abelian category of sheaves on a non-commutative elliptic curve. This is work by Polishuk. So they have some geometric meaning in the non-commutative world, and I would expect something similar here, only that it is not clear what the non-commutative K3 surface in explicit terms should really be. Okay. And the last bit of motivation is the theorem of Bridgeland, actually showing that if there is any stability condition with some of the nicest property you could have, or some of the, a very basic property, then the heart of this has to be this category. So this is the following theorem. So if sigma is a numerical stability condition on dB co-x, so x as before, a smooth projective or a compact complex. Works in most cases, such that, so I should say before I state this, the theorem, so when we have a stability condition, then we have the heart, and then as Marcus explained, we want to look at moduli spaces of objects in the abelian category, and so for instance moduli spaces of sheaves, moduli spaces of line bundles on the variety, but so the easiest moduli space on any variety is the variety itself. And the variety itself is always the moduli space of closed points on the variety. Okay, so if I want to first to study stability conditions such that the easiest moduli space is in fact the moduli space of stable objects, then I would require that for all closed points in X, Kx is stable, so sigma stable of phase 1. This is just a normalization of phase equals 1. Then it's hard, the hard A sigma, which by definition is everything that has phase in 0 and 1, between 0 and 1, is actually this abelian category I constructed as a tilde for some real number beta and the class omega, which is at least nef, which satisfies omega c positive for all curves in X. Okay, so if some of the easiest sheaf on the surface are required to be stable of constant phase, then the heart of the stability of the numerical stability condition can nothing be else than this tilde of the coherent sheaves. Okay.
Are you asserting that such a stability condition always exists?
No. No.
What does that first letter say then?
This one?
Yeah.
This was an if. This was the beginning of an if. Sorry. No, that's so I'm inverting the strategy. I'm not constructing things, but I'm classify first, and then. No, this is surfaces. Point sheaves? Okay, so this is somehow if I introduce stability conditions on a category in order to afterwards study moduli space of stable objects, right? Then the moduli space of point sheaves on the variety would be like the easiest moduli space. And somehow I put this as a requirement on my stability condition. I want somehow I want to recover the variety itself, the surface itself, as the moduli space of stable objects with respect to the stability condition. Of course, not of course, but there like on K3 surface, there are other stability conditions, but these are somehow supposed to be the easiest ones. I'm about to classify some of the easiest stability conditions on the surface. Right?
Why do you insist they all have the same thing?
That is, that again, that's not automatic. But if I want my variety X as the moduli space of sheaves, then the object, the moduli space parameters all have the same phase. Otherwise, it wouldn't be moduli space. It's a moduli space of stable objects of a given phase. Right? Okay. So now I actually want to prove this. At least I'll break this up in a few steps and prove some of them. Say again? I didn't get the beginning of your sentence. Yeah? Right. Now then, you should think of the numerical data as being discrete, right? So you have this discrete race of stable objects. So if you allow the phase to vary, the moduli space would just be a disjoint number of disjoint union of number of moduli spaces. I mean, in a way, what Markus will do in his course on Hall algebras, he will actually allow different stable objects of different phases and look at the extensions and to define the Hall algebra. But if you just talk about one moduli space, then the phase will automatically be fixed. Okay. So I break this up in 5 claims. So the first claim is so I want to study the objects in the heart of the stability condition and see how far they are from being sheaves. So the first claim is if I have an object in the heart, then it is concentrated in degrees 0 and -1. So then this is 0 except for 0 and -1. And moreover, H minus 1 of E is torsion free. Okay, this is first part of claim 1, and the second part is I can actually classify the stable objects in of phase 1. So if this is stable, then, well, at least all the point sheaves are stable of phase 1 by definition, by assumption. Either this is Kx, or it is of the form F shifted by 1, where F is a locally free sheaf. Okay, so let's try to prove this. So here's a standard technique. I'm looking at the morphisms from. So let me see. Okay, so I can suppose that. No, we can assume that E is stable and not isomorphic to Kx. Why? So we want to show that an object in the Siberian category has cohomology only in degree 0 and -1. I can use the Harder-Simon filtration or the Jordan-Hölder filtration to break it up, and then it is enough to show that this condition here holds for the factors in the filtration, right? Just the usual thing. Because somehow, like if it has 2 stable factors, then these cohomology sheaves will be sandwiched between the cohomology sheaves of the 2 stable factors, and if those are concentrated in degree 0 and -1, then the cohomology of E will. So I can assume E is stable, and I have nothing to do if it's actually a point sheaf, so I assume it's not the point sheaf. And now I have 2 stable sheaves, and the phase of E is in the interval 0, 1. So in particular, there won't be any morphisms from E to Kx for I smaller than 0. Why? Well, this is I can write this as homomorphism. And then this will have the phase of E shifted by I will be in the interval I plus 1. Am I do what? That's much better. Yes. So this will be minus I. I'll get confused. So if I shift it by minus I, then the phase will be in minus I and 1 minus I. Why am I saying this so strangely? I want this to be 0 for negative I. Yeah, of course, yeah. So for negative I, for negative I, this is actually positive, right? This is actually, this minus I then is at least 1. Then the phase of this one is actually bigger than 1. But there's no morphism from a stable object of phase bigger than the phase of Kx. Okay, so that one is 0. And then similarly, I can argue the other way around. Kxe is 0 for I smaller than or equal to 0. And the same argument, and by Serge-duality, this is isomorphic. I get that xi of e to kx is 0 for I bigger than or equal to 2. So these two things put together, I find that there are no x from e to kx for except maybe for I equals 0 or 1. For I. Okay. So how can we use this to control the cohomology? Well, one thing you can do is look at the spectral sequence e to pq going from xp h minus q of e kx to xp plus q from e to kx. So these two things here are sheaves. So there are no negative x between sheaves, and since I'm on a surface, there are also no x for p bigger than 2. So if I draw the diagram for this spectral sequence, so there's p here, and there's q here, 1, 2, 3. So 1 is 0, 1, 2. Everything right from this will be 0, just because the p is too big, and there won't be any negative x, so it will be 0 on this side. Now, if I let I be the maximal degree of non-trivial cohomology, and similarly j the minimum, then this appears here as minus j, and down here as minus I. And above it, everything will be 0, and below everything will be 0 as well. Okay. So this is the spectral sequence, and now the differentials on the E2 level, they go like this. And in particular, you see that these things here will survive all the differentials. And similarly here, because the target of these differentials will always be 0, so these 4 boxes, they survive. So getting confused. Yeah. What's my spelling of survive? Is this right? It looks like French to me. Is this right? Okay. So they survive to infinity. So, but now we know that the limit here is only non-trivial for, so this is 0 for p plus q, not 0 or minus or 1. So this means, if this, for instance, if this box here survives, this has to be, this means that minus I can only be, oh no, sorry. Sorry, again. So now, since we know that hi of E is non-zero by definition of E, there exists a point. I mean, this can be a sheaf that can be a vector bundle, it can be a sheaf concentrated on a curve, can be concentrated in some points, but there's always one point in X where there's a homomorphism from Hix, Hie to Kx. Right? Take any point in the support of the sheaf, and then there will be non-trivial morphism, and this means that this here is always non-zero. Right? But if it is non-zero, then also x I will be non-zero, and then I has to be 0 or minus 1. I'm sorry, this is q, so this is minus 1 minus I. So the top cohomology will be either in degree 0 or in degree minus 1. But then so I allow myself to choose the point accordingly to depending on the support of E. Okay, so now believing there's a similar argument that actually shows, I mean, applied to these boxes upstairs, one proves that actually J has to be 0 or minus 1, and that means that indeed E is concentrated. E is concentrated in degree, in degree 0 minus 1. So this proves the first, the very first part here, that's only concentrated in 2 degrees. Let's see what we can say about this H minus 1. Why is H minus 1 torsion free? This also comes out of the spectral sequence. So if H minus 1 has torsion, the torsion can live in dimension 0. If it lives in dimension 0, then there exists a point such that Kx is a subsheaf of this torsion. So in particular, there's a morphism from Kx to H minus 1 of E, and this is Serre-Joule to X2 of H minus 1 E Kx. And this means that this box here, this one will be 0, and this implies that X3 of E Kx is non-zero, which contradicts what we've seen before. And similarly, for the case that H minus 1 is torsion in dimension 1, then there exists actually a point where X1 Kx H minus 1 of E is non-zero. And again, by Serre duality, this is isomorphic to to X1 H minus 1 E Kx. And this would mean that this bit here is non-zero, and this would imply that X2 of E to Kx is non-zero, which again is a contradiction. So this, I mean, this is pretty clever to really use the spectral sequence and the information we have about the limit actually to show to use facts for its cohomology. Okay. And let me not prove maybe this part 2 of claim 1 that uses again this the spectral sequence. So that's maybe I should rephrase this claim 1 as saying that if A is a semi-stable sheaf of phase phi, then it has no cohomology if I is non-negative and the phase is bigger than 1, or I non-positive and the phase is smaller or equal to minus 1. So this is by shifting the heart around, then you find this this reformulation. Okay, so let me give you at least some of the other steps. So the first claim was showing that elements in the heart have a certain property. So they're not far from sheaves, they're only concentrated in 2 degrees. Now, to go the other way around, Friedrich proves that if I have a coherent sheaf, then it also is concentrated in essentially in 2 degrees with respect to the stability condition, namely E is contained in this heart. Not in the heart, but in so if you look at its image in the plane, then this would be the whole plane, contrary to the upper half plane, which is the image of the heart. Okay, and part 2, if it's in addition torsion, a torsion sheaf, then in fact it is in the heart itself. Okay, try to indicate at least what goes into the proof of this claim. So in order to show that a certain object, so here a stable coherent sheaf, lies in this category, I have to show that the minimal and maximal destabilizing phase are between -1 and 1. So if I have to show that phi of A1. So remember, so if I take the Harder-Simon filtration of E, then this goes like this: A1, A2, A2, and so on until En. And the phases are strictly decreasing. And we have to show that this one is smaller or equal to 1, and this one is at least -1. This is what it means to be in this category, and let me prove that the maximal one does not exceed 1. Yeah. So if I take A1 as above, so this is the maximal slope of E. So then this morphism is clearly non-zero, and hence, so this is a sheaf, and this is a complex. Then there's at least one cohomology of this sheaf which maps non-trivially to E. But clearly this means that the I has to be non-negative, because these are now 2 sheaves, and that is an extension of degree I, and if the I is negative, there are no negative extensions between sheaves. So the I has to be, so there exists an I such that it is non-zero, and hence the I has to be at least 0. But on the other hand, I have this claim up there, and this proves right away that the phi of, I mean, if this morphism is non-trivial, then in particular this one is non-trivial, and hence the phi of A1 has to be less or equal to 1. And similarly prove the other inequality, this one, by using the quotient of E to AN. So this kind of argument you use to show that the objects in the abelian category of coherent sheaves are not far from objects in the heart. And then you can actually define, so this is step 3, you define a torsion theory T in the standard heart by saying T is everything that lives in both hearts, and F is everything that lives in the heart, in the standard heart and the shifted heart of the given stability condition. And then it's actually not difficult to prove that the tilt A with respect to this torsion theory is the given hard P01. So this is, if you want, this is a general fact I mentioned in the tutorial, which you find in this memo of Beligianis and Reiten, that shows that T structures that that are not too far from a given one have hard, which is obtained, can be described in terms of a tilt. So that step is not difficult, but we are not done yet, because I found the torsion theory describing the given hard, but I've not described this torsion theory explicitly, right? So the claim, of course, of the theorem is that this one is the torsion theory I have defined over there. So I've not yet, still have to show that T is T omega beta. And for this, actually, I have to find the omega beta. So we have not yet talked about the omega beta at all. Okay, so I have to make a choice now. So you see, I mean, for surfaces, the proof is a bit longer. So the next step would be, step 4 would be to say, well, the given stability condition is numerical. So this is given by a slicing and a stability function. And being numerical means that this function z can be written in terms of the pairing on the level of cohomology. So, so there's something in H0, there's something in H2, and there's something in H4. And then I cup it with like the rank of E, churn 1 of E, and churn 2 of E. And I can use here, so the standard way to do this is actually to use the intersection pairing with a sign between H0 and H4. So this is essentially the intersection pairing on cohomology. So this is what it means to be numerical, that the value of Z of a sheaf only depends on its numerical invariance, and since the intersection pairing is non-degenerate, I can actually write it as an intersection product on the cohomology. Okay. Now, for E equals kx, what is this vector here? This vector is actually, its rank is 0, it has no first Turing class, and the last one is 1. Okay. So now our assumption that kx are stable of phase 1 means that Z of kx is a negative real number, and that means that this thing here has to be a positive real number. The important thing is it is real, and that means its imaginary part can be written as something. So there's nothing imaginary here, so it's 0 here, and then there's the class omega here, and there's a class in H4 which I interpret as a number, as a real number, beta. Okay, and here I find my omega and beta. This is how I get the omega and beta. If I didn't assume that the stability condition was numerical, I wouldn't know how to find this class omega and beta. And then one shows that omega c is actually positive for all curves. And this is almost, I mean, it's almost as good as saying that omega is ample, but not quite. So what we get this this condition. Okay, I'm about to wrap up. The last step then is to show that if I have a mu stable sheaf, mu stable torsion-free sheaf, then I can decide exactly when it is in T. Namely, it's in T if and only if its slope with respect to this omega here is bigger than beta, and it is in F if its slope is small or equal beta. this again, I mean, this needs a proof. It's not long, but still needs to be proved. And once I have this, I find that the torsion theory I've defined in the beginning is actually contained in the torsion theory that I have defined in terms of the given stability condition. So, and if I have an inclusion of torsion theories like this, then this immediately implies that they are equal, and in particular their hearts are the same. So this is very briefly the proof of Bridgeland's classification result. But I stress again that I actually have not shown the existence of any stability condition on the surface yet. Okay? So if there is one, then we know it. I mean, having this nice property that the point sheaves are all stable of the same phase, then we know at least what its heart is. But maybe I finish with a corollary. If X is a projective surface, then the standard heart can never be the heart of a numerical stability condition. So this is a bit disappointing. It worked nicely for curves, but for projective surfaces, the standard T structure is never the T structure underlying a numerical stability condition on the surface. And in fact, it's not. So for K3, so for non-projective K3 surfaces, this is not true. So if X is a K3 surface, not projective, which I measure by its Picard number, so trivial Picard number, there exists a stability condition on the standard heart, stability condition on coax. So it's really about the projective surfaces. Okay, so if you're in algebraic geometry, there's no problem. And why is this a corollary of the classification result? Well, if I suppose I have a stability condition on the standard heart, then what are the minimal objects of this category? Well, I mentioned this before. These are the point sheaves. So then automatically the point sheaves will be stable all of the same phase, and you can actually assume that the phase is 1, and that means this heart has to be given by this tilt with respect to this torsion theory. This is the theorem we just proved, but on a projective surface you can show that there's always a stable bundle, mu stable bundle of a very negative slope, and hence there will be something in degree -1 in this heart of the T structure. But of course, in the standard heart, there is nothing in degree -1. So you get a contradiction like this, and maybe this is a good point to stop.